Hi, everybody. My name is Ben Blum. I was an intern on the Rust team this summer, and I did a bunch of assorted work, some of it on the type system and some of it on the runtime. And today I'm going to talk to you about the type system because the work I did on that is a little bit flashier. As you can see, the presentation is called Types of Types in Rust, and I will soon explain what that means. So first, I'm going to give a little overview of what types of types, also known as kinds, are in Rust. I'm going to talk about how they interact with traits, which is our interface, type class, object, everything that is great in one package, part of our type system. And then I'm going to get a little more focused and talk about how they can be used as existential types and the work that I did to make them a little friendlier with our kinds. Then I'll talk about the specific stuff that I did, and I'll give some motivation and tell you why it's great, and instead of just not wanting to do it at all, why I did want to do it. Before I get started, I will make an announcement, which is that we have a new runtime, and it is written in Rust. I remember getting here last summer, starting to work on the C++ runtime, and noticing that our compiler was written in Rust. So, well, why don't we just switch over to Rust? Well, that would be a lot of work. So I just, did a bunch of C++ work last summer. But now it's really exciting because not only are we self-hosted in the compiler, but also in the runtime. I spent a bunch of weeks doing runtime work, but as I said, it wasn't very flashy, and it was basically just implementing behind-the-scenes plumbing to make the stuff that I implemented last summer still work on the new runtime. And if you want to learn about the stuff that I did last summer, well, you can go on Air Mozilla, go back a year, and find me there. That's me, teleported forward in time a year to bring to you this one slide image from last. Anyway, yes, moving on. OK, so what are kinds? In the type theory lingo, kinds are types of types. That is, sort of a language of various descriptors that apply to types in the same way that various descriptors that are types, like integer or list of some other type, apply to terms and values. What's my next? Oops. All right. Yes. So in Rust, we don't exactly have kinds in the strictest sense of the type theory interpretation. So if there are type theorists out there, please don't get mad at me for using a bunch of terms willy-nilly. But in Rust, we have these things which we call kinds, which describe capabilities of types. And they are sort of built-in language items that the compiler knows about internally. And they are as follows. There's the send kind, which describes data that you are allowed to send between tasks. And this is the mechanism by which Rust's type system guarantees that tasks running in parallel can't access the same state, and that everything has to be communicated with message passing. There's the freeze kind, which describes a type that has no mutable interior. In Rust, mutability is part of a type, and if a type doesn't have any mutability inside of it, then it satisfies the freeze kind, which means that as long as it's stored in an immutable location, the entire thing is immutable. You can't mutate any part of it. There's the static kind, which is reasoning about the lifetime of certain data, meaning that it will never go out of scope. For example, a pointer to something that lives on a stack frame or a garbage collected pointer doesn't fulfill the static lifetime. Only sort of global constant values can fulfill the static lifetime. There's also the copy kind, which means you can implicitly copy this. Stuff like owned pointers, because to copy those would require a deep traversal of the entire type and copying the whole thing. That doesn't satisfy copy, but stuff like integer or garbage collected pointers, those are fine to copy. Actually, the copy kind is dead. Long live the clone kind. But for the sake of this presentation, assuming that the copy kind still exists will make explaining some things easier. So I'm assuming that it still exists. All right, so the nice thing about KindBounds is usually you don't have to worry about them. They're automatically derived by the compiler. So if you write a type, such as an option of a t, the compiler automatically derives, do you want to satisfy some kind k with this option of t? Well, as long as t satisfies it, then option does too. How are they used? Here's some examples to get them into your heads. I mentioned message passing and send are linked. In fact, the message passing interface explicitly uses the send kind because the message passing has unsafe internals. Putting send on the interface is sort of the glue that makes it all safe on the outside, safe to the users. So if you want to do message passing, this is a basic interface. You have a function which will give you a stream, which is a pair of a port and a channel. A port is a thing you receive on. When you receive on it, you get a t, where a port is parameterized over t. And a channel is this thing that you send on. When you send on a channel, you have to give it a t. Pretty simple. Yes, the send bound ensures that once one task sends data on a channel, that's data : t there on the bottom line, that task is no longer allowed to access it. The only task that will be able to access it is the receiver. In effect, it means the sender is giving up ownership of the data. Now on to the freeze kind. This is useful for an interface which allows you to share state between tasks, because if you only have message passing, you might have to copy large vectors of things more times than you have computational power for. You might instead want to share stuff. We allow you to share stuff as long as you can reason about it being immutable. We have a type called arc, which stands for atomically reference counted wrapper. And you can put stuff in an arc as long as it satisfies both the send bound and the freeze bound. If you have an arc, the second line means you can clone an arc to get a second handle, and both handles will point to the same underlying state. And the way you access the state is with the get function. You call get with a pointer to your handle, and it gives you a pointer to the underlying data. The tick A on the pointers means that the lifetimes are tied together. I'm not going to worry too much about this in the presentation, even though it's really cool, because I don't need to worry too much about lifetimes. But in any case, this interface sort of allows you to share immutable state across tasks. And it is safe thanks to the two kind bounds. Send ensures that once you construct an arc, the only way to access the data is through the handle. And the freeze bound ensures that when you're sharing it across tasks, nobody's ever allowed to mutate it, which would cause data races and crashes and seg faults and so on, and security vulnerabilities. We don't want that. OK. On to section 2. Time to talk about traits. Traits are type classes. Traits are interfaces. If either of those words mean anything to you, traits are both. My example trait here, it's going to be a running example, is pet. Anything that implements the pet interface has a name. It also has a number of legs. And it also has a function which will determine whether or not the pet is well behaved. You can also use traits as objects. Object-oriented programmers will be very familiar with this. In Rust, here's what this looks like. Let's say we have a struct dog, and dogs have names, and dogs also have a number of decibels, which is the loudness with which they bark. There's an implementation of the pet interface for dog, and I've elided the implementation, but you can imagine. And now I have a value, Alan Turing. Do you have a dog named Alan Turing? No. Okay. Only we're making believe. Okay. Only in the scope of this presentation. I also do not have a cat named Ada Lovelace, nor a bird named Albert Einstein, okay. As we will see later. Anyway, we're making believe that I have a dog called Alan Turing. and the dog initializer is elided, but pretend it's there. And on the last line, what I'm doing is I am casting Alan Turing to a generic pet. So you can use this generic pet object as though it were a pet. You can get its name, you can get its number of legs, and you can ask if it's well behaved. But you can't do dog-specific things with the generic pet. That would be wrong. So when you do this, it generates a virtual table of function calls on the spot for the generic pet value. Back to type theory lingo for a moment. This is an existential type. It means sort of an opaque type that presents a generic interface. And in really formal type theory lingo, it is pronounced, there exists some x of type T such that some interface of x. Again, object-oriented programmers will be familiar with this as just treating an interface as an object, which in C++ always generates a vtable. I'll take a moment to point out that closures in Rust are sort of a special case of trait objects. The value of a closure is the environment, that is the values that are captured in the closure. And the trait for a closure would, if it existed, look something like this. There is one function, and it is call. It takes some arguments, and it returns a value. So everything that you can do with traits that I'm talking about in this presentation, you can also do with closures. But I'm going to focus on traits because closures are just a special case. So I'm not going to bother to present what it would look like for closures also. In Rust, a key thing about traits, trait objects that is that they're dynamically sized. When you create a trait, you generate a virtual table of function calls, and you also have the value next to it, a dog. But you might also have a generic pet that's a bird. And well, a bird is smaller than a dog, so the trait object for a bird would take up less space in memory than a dog. So if you want to carry around these traits in Rust, you have to hide them behind a pointer. A bare trait itself is not a type. So like in the previous slide, I wrote ampersand pointer to Alan Turing as pointer to pet. You're not allowed to do that without the ampersands, and I'll continue to do it in the rest of this talk. OK. So now let's talk about what's contained inside opaque object types. First, before I happened to it this summer, there were some defaults, and you couldn't really budge them. You had to use them as they were. If you were using an owned pointer to a trait object, it can only contain sendable values. And this is what enabled you to send opaque traits between tasks. The guarantee that a tilde trait would only be sendable, and you could only construct one out of sendable values. A garbage collected managed trait can only contain static values, because the garbage collector can delay trying to clean up something at any time, or as long as it wants, rather. And if you had pointers to stuff on your stack frame, otherwise capturing such a pointer inside of a garbage collected trait would let it escape and cause crashes. Using an ampersand trait can contain any value. And consequently, you can do the least amount of things with it. Also, traits are never freezable or copyable. The type system didn't really allow you to reason about whether a trait contained interior mutability or not, which was unfortunate. So I fixed it. And I fixed it with a mechanism that is called KindBounds. Like putting KindBounds on a type parameter to a function, which I presented earlier in the message passing interface and so on, now you can also put KindBounds on a trait, on a type itself. So thanks to me, if you want to reason about the stuff that's contained inside of an opaque trait, you can write the name of the trait type, tilde pet, colon, whatever bounds you want. So if you write tilde pet colon copy, this means the restriction on the construction site of such a thing that you can only put copyable values in it. And on the usage site of such a thing, it gives you the capability to copy it. Likewise, the analogous restrictions and capabilities apply for the other built-in kinds. All right, so I'm going to make a non-copyable Alan Turing. And I'm going to assume that the stuff inside the dog initializer is non-copyable, which makes him non-copyable. So this is, on the second line, I have the same cast as before, a generic pet, which is non-copyable. And on the third line, I'm trying to make a copyable pet out of non-copyable Alan Turing. And now the compiler will give an error that says, cannot capture non-copyable value in trait bounded by copy, because I tried to violate the restriction imposed by the bound. OK, so what is this good for? This is the motivation slide. And if you take one thing away from this presentation, I would like it to be this bolded bullet point, which is that now, thanks to the various concurrent data structures we already have, you can now match up KindBounds on your trait objects with KindBounds required by our concurrent data structure interfaces. So I'm going to give an example, which is sharing lists of objects between threads. And specifically, what I mean is sort of heterogeneous objects. That is, I have a list of a bunch of pets, but the specific implementations of pets among the different elements in the list could be whatever. All right, so I have Alan Turing, which is a dog. I have Ada Lovelace, which is a cat. And I have Albert Einstein, which is a bird. And presumably, they all have their own numbers of legs and their own well-behavedness and their own name. And now I'm going to put them in a list. I'm casting each of the three of them to a pet, which fulfills both the send and the freeze bound. And I'm assuming that in the construction of them, they fulfilled that bound. So now I have a list. And since on primitive types like list, KindBounds are automatically derived, we know the whole list satisfies send and freeze. So now I can pass it to the arc constructor. And I can now clone the arc and share it among threads. And now all my different threads are sharing handles to the same underlying list to a bunch of different types of pets. Voila. I will end with a bit of perspective, sort of about Rust's mission, by posing the question, well, can't C++ already do this? You could just make a list of objects, which is really easy in C++, store that in a global location or whatever, and spawn off a bunch of threads to access it. So I don't get it. What's so great about being able to do it in Rust? Like, duh, you should be able to do this. And my answer to that is, well, C++ will sort of always be more expressive than Rust in certain ways, because Rust tries to provide, static safety guarantees, and it's harder to have certain features. So what this really means is that we are rising to the challenge of being as expressive as C++ in certain features without compromising on our safety guarantees. In this case, no data races, because if you did the same thing in C++, there would be nothing to statically prevent, mutating the pets, giving them a dog treat or whatever, while other tasks were accessing them, which would cause security vulnerabilities. So, hooray! We have risen to the challenge, and I think that's really great. I would like to thank certain people. First and foremost, in no particular order, well, in alphabetical order, I will thank Brian Anderson and also applaud him on the heroic effort to have a runtime written in Rust, and also thank him for the guidance that he provided while I was working on the runtime this summer. And next, I will thank Nico Matsakis, my mentor, who helped me get familiar with the internals of the compiler, helped me understand the underlying type theory issues pertaining to all the various things that I needed to consider while implementing the trait stuff, and things that are still unimplemented. I would like to thank the other interns that I worked with for their heroic efforts on the runtime and servo. 2 of you are sitting right there. More of you are sitting right there. The 2 Rust ones are sitting in the front and a servo one in the back. And of course, the rest of the Rust team for being a great community and for being really supportive. It's really a pleasure to work with you guys, and I hope that it doesn't end here. Come at me.
Can you elaborate on the clone?
Clone, yes. So yes, copy is dead, long live clone. Clone is sort of a better version of copy in that it allows you to provide a user-specified implementation. So for example, in the case of Arc, you don't just want to copy it. The clone implementation of Arc needs to do management of the atomic reference count. So the Arc library uses the clone trait to actually manually write such a thing. The consequence, however, is that whenever you want to call clone on something, it's not just something that the compiler can automatically generate code for. It has to generate a call to perhaps some user-provided stuff. So in particular, if you wanted to put the clone bound on a trait or on a closure, that would require emitting another entry in the vtable for clone. And we don't have code to do that yet. We want to, but it's hard because it involves more code generation. Anything else? Thank you.